Hello everyone. We come to the last section of factor group computations and simple groups. In the previous classes, we have seen different types of factor group computations. And now we see different types of normal subgroups of a group G. So let G be a group, then we know that the identity element itself is a normal subgroup of G, and we call it the trivial normal subgroup of G. If we consider G itself, it is also a normal subgroup of G, and we call it the improper normal subgroup of G. Now any subgroup other than G and E is called a proper non-trivial normal subgroup of G, provided it satisfies the conditions of a normal group. That is, if A is an element in G and N is in A and A inverse is in N. We call a group simple if it contains no proper non-trivial normal subgroups. That is, E and G are the only normal subgroups of G. An example is that the alternate group AN for n greater than or equal to 5 is simple, and the cyclic groups of prime order are also simple groups. In fact, they are simple abelian groups. We now go to a theorem to see how homomorphisms act on normal subgroups. That is, if n is a normal subgroup, then phi of square bracket of n is a normal subgroup of phi of square bracket of G. So let this be G and let this be G dash, from where this homomorphism is defined to. And you consider phi of square bracket of G. So you have phi of square bracket of G, and you need to prove that if n is a normal subgroup of phi of G, then phi of square bracket of n is a normal subgroup of phi of square bracket of G. So in order to prove that, you need to start with an element in phi of square bracket of G and an element in phi of square bracket of n. So let phi of A is in phi of square bracket of n, which means that there is an A in capital N such that phi of A is in phi of square bracket of n. Now if G in G and A in N, we know that GA G inverse is an element of N. Since N is a normal subgroup of G, we need to prove that phi of G into phi of A into phi of G inverse is in phi of square bracket of N. Now this is same as if you compute one more step, you will get it as phi of GA G inverse. Since GA G inverse is in N, this phi of GA G inverse must be in phi of square bracket of N. And hence we proved that phi of G into phi of A into phi of G inverse is in phi of square bracket of N, which proves that the phi of square bracket of N is a normal subgroup of phi of square bracket of G. Now in order to prove the other part of the theorem, so let n dash be a normal subgroup of phi of square bracket of G, and we need to prove that phi inverse of n dash is a normal subgroup of G. So here let x be an element of phi inverse of n dash and G in G. Now we need to prove that Gx G inverse in phi inverse of n dash. Now we say that x is in phi inverse of n dash since phi of x is in n dash. So in order to prove that Gx G inverse is in n dash, we need to prove that phi of Gx G inverse in n dash. So let us start with the phi of Gx G inverse. So you can see that after one step of computation, that is same as phi of G into phi of x into phi of G inverse. Since n dash is normal and phi of G and phi of x are respectively elements of phi of square bracket of G and n dash, we get this belongs to n dash. So since this belongs to n dash, we have Gx G inverse in phi inverse of n dash. So we proved the second part of the theorem. Now remember that in the first part, we need to prove that phi of square bracket of n is a normal subgroup of phi of G and not G dash. Why? Because you can see there is a counter example. Consider phi from Z2 to S3, where phi of 0 is rho naught and phi of 1 is mu 1. And here you can see that phi of Z2 is not a normal subgroup of S3, which plays the role of G dash here. Now let us see a definition. A maximal normal subgroup of a group G is a normal subgroup capital M which is not equal to G such that there is no proper normal subgroup capital N of G properly containing M. That is, M not equal to G and there exists no N or M dash which is normal in G such that M is properly contained in M dash. So we can ask a question, if G is simple, what about the maximal normal subgroups of G? If you know the answer, give it as a comment to this video. Now we go to the next theorem, that is M is a maximal normal subgroup of G if and only if G over M is simple. The proof is simple if you consider the homomorphism from G to G over M, which takes some small g to G capital M, and with the kernel of gamma is equal to M. Remember that kernel of gamma is the collection of all elements in G that are mapped to the corresponding identity element in G over M, which you know that is equal to M. Now we start by assuming that M is maximal, but G over M is not simple, which means that there is a non-trivial proper normal subgroup of G over M. Now since N dash is non-trivial, it contains at least one element other than the identity element. Also since it is proper, it contains at least one element outside that N dash. Now you consider phi inverse of N dash. Now we are going to prove that it properly contains the normal subgroup capital M. For you can see that phi inverse N dash contain at least one element which must map to the additional element in N dash other than E. And since there should be an element outside this phi inverse N dash that should map to the element outside N dash, you can see that phi inverse N dash is not equal to G and properly contains capital M. So we can see that this statement contradicts the maximality of capital M, since we know that phi inverse N dash is a normal subgroup. So we have a wrong assumption, that is our assumption that G over M is not simple is wrong, and we have G over M must be a simple group. Now conversely, let us assume that G over M is simple. We need to prove that M is a maximal normal subgroup of G. So let us assume that M is not maximal, which means that there is an M dash which is not equal to G such that M dash is normal and properly contains capital M. Now you consider gamma of M dash. Since M dash properly contains M, it contains at least one element other than capital M, the elements of capital M in M dash. And also since it is proper, it contains an element outside of it, which means that gamma of M dash contains at least one element other than the identity element, and also it is proper in G over M. Thus we have gamma of M dash is a proper non-trivial subgroup of G over M, but that is a contradiction to our hypothesis that G over M is simple, which cannot have normal proper non-trivial subgroups. So our assumption that M is maximal, M is not maximal, is wrong. So M should be a maximal normal subgroup of G. Now we finally arrive at two types of normal subgroups of a group G, that is center and commutator subgroups. The center of a group Z of G is defined by Z of G is equal to set of all Z in G which commutes with all other elements in G. So it is clear that Z of G is an abelian subgroup of G, for which you can prove the different properties required. That is, you can prove that it is closed, for which you can start with an x in the center Z of G. Then you have xg is equal to gx for every g. And if y is an element in the center, then y commutes with all other elements. In order to prove that xy is in the center, you need to prove that xy into g is same as g into xy. So you can prove in just 2 or 3 steps, and hence you proved that xy is also an element in Z of G. Next, you can prove that the identity element E is in center, for which you already know that the identity element computes with all elements in G. And if X is an element in the center, you can say that X inverse is also in the center, for which you know that G inverse X is equal to XG inverse. Taking inverse on both sides, you get the condition required for X inverse. So thus we proved that Z of G is an abelian subgroup of G. So if G is abelian itself, then you can see that Z of G should be equal to G, and we say that the center of a group is trivial if Z of G equal to the identity element. Now you consider an example, that is S3, and let us calculate the center of S3. If you consider the column and row corresponding to the element row naught in the table structure of S3, you can see that the row and columns are the same, which means that row naught is an element in the center of S3. Now you can see that there are no elements satisfying this property, and hence you can see that center of S3 is row naught only, the identity element only. Now since center of the abelian group Z5 is Z5 itself, you can calculate the center of S3 cross Z5 as rho naught cross Z5. Now this is an introduction to the center of a group. Now let us go to the next topic, that is the commutator subgroup of a group. Now what is a commutator? An element of the form AB, A inverse, B inverse in a group is a commutator of the group where A and B are any two elements in the group. For example, if you consider the identity element E, it is a commutator. Why? Because you can write E as A inverse, A inverse. Here B is equal to A. Now the smallest subgroup containing the set of all commutators is called the commutator subgroup of G. That is, it is generated by the set of all commutators. Now we usually denote it with C. So let C be the commutator subgroup of G. You can easily prove that this is a normal subgroup of G. Since it is a subgroup generated by the set of all commutators, we just need to prove that C is normal in G. That is, you have to start with an element X in C and G in G, and you need to show that G inverse XG belongs to capital C. Since X is a commutator, it is some CD, C inverse, D inverse. So you need to show that G inverse into CD, C inverse, D inverse G is a commutator, or it is enough to show that it is a product of two commutators. So we start with G inverse into CD, C inverse, D inverse G. By associative property, you can have it as G inverse CD, C inverse into D inverse G, and you can add an E in between, and this E can be replaced with G into D inverse D into G inverse in the next step. So there is no change in this expression. Now in the next step, we find two commutators. The first commutator is formed by G inverse C and D. That is G inverse C into D. Then you can have the inverse of G inverse C, that is C inverse G and D inverse. The second commutator is formed by D and G inverse. That is D, G inverse, then inverse of D and inverse of G. So rearranging the brackets, you can now clearly write the expression on the right hand side as a product of two commutators. The first one is obtained by G inverse C and D. Then you can have their inverses. The second one is obtained by D and G inverse, and you can have their inverses in the order. So you proved that G inverse XG for a choice of X is equal to CD, C inverse, D inverse is a commutator, and hence we proved that C is a normal subgroup of G. So when you have a normal subgroup, you can think about the corresponding factor group G over C. Now is it abelian? Now the required properties AC into BC should be the same as BC into AC. So the proof is given here. The only thing you need to notice that C contains all its commutators. So there is a step where you replace C with B inverse A inverse BAC. So you can see the corresponding steps here, and just rearrangements of the brackets and the terms, you can obtain the result. So you proved that when C is a commutator subgroup, it is normal and G over C is an abelian group. Now we have the final result. So you need to prove that G over N is abelian if and only if C is a subgroup of N when N is a normal subgroup of G. So we start with assuming that C is a subgroup of N. So let us write if C is less than or equal to N, that is if C is a subgroup of N, then G over N is abelian if a condition is satisfied. What is the condition? An into Bn is equal to Bn into An. Now the steps required are just similar to the previous one. That is, since N contains all the commutators, we have N can be replaced by B inverse A inverse BAN, and if you rearrange, you can have it as the product of E into BAN, and BAN is BN into AN. So you proved that if C is a subgroup of N and N is a normal subgroup of G, then G over N is an abelian group. Now as the converse, we assume that G over N is abelian, and you need to prove that all commutators are contained in N. Since G over N is abelian, you can have A inverse N into B inverse N is equal to B inverse N into A inverse N, the commutative property. Now this is same as writing A inverse B inverse N is equal to B inverse A inverse N. If you multiply both of these sets with AB, you can have AB A inverse B inverse N is actually En, that is N. Thus you proved that an arbitrary commutator AB A inverse B inverse is in capital N, and since the commutators form a subgroup, you have C is a subgroup of N. And now you can see an example. Consider S3, and what is the commutator of S3? What is the commutator subgroup of S3? If you note rho naught, rho 1, rho 2, which are members of A3, you can see that rho naught is a commutator since it is the identity element, and you can obtain rho 2 as rho 1 mu 1, rho 1 inverse mu inverse, and you can obtain rho 1 as rho 2 mu 1, rho 2 inverse mu inverse, which means that A3 contained in C, or A3 is a subgroup of C. Now we already know a theorem, that is G over N is abelian if and only if this commutator subgroup is a subgroup of N. Now here if I replace N with A3, since N is a normal subgroup, you can have G over A3 is abelian, and that is true, and you can have C is a subgroup of A3. So from these results you can have C is equal to A3. Thus we have the commutator subgroup of the group S3 is A3, and we used the previous theorem to compute the commutator subgroup. Now you have two problems and try to compute the answers. So thank you.